Welcome to this forest glade, where a group of aspiring archers are learning and practicing their craft. With their help today, we will be learning all about the Frank Starling law of the heart, which describes how increases in venous return and the end diastolic volume will lead to increases in stroke volume and cardiac output. Put more simply, it is the mechanism by which cardiac output, how much blood leaves the heart, is matched to venous return, how much blood enters the heart. It is based on the length tension relationship in cardiac muscle, which describes the effect of increasing ventricular muscle cell length on the amount of force generated during contraction. You may remember hearing about a length tension relationship in skeletal muscle, which is similarly related. This relationship is depicted here by this rack of four different size bows. You'll notice that the short bows have bowstrings under little to no tension and would struggle to shoot even short distances, while the longer bows have bowstrings under high tension that would let them shoot much further. The length tension relationship states that the amount of tension or force a myocardial cell can generate depends on the degree of overlap between the thick myosin and thin actin filaments of the sarcomere. This teacher, Mike, is helping his student, Ace, draw his bow back to help you remember this. Note how Mike's thicker arms are overlapping with Ace's thinner arms. The more overlap between filaments, the more sites there will be for actin-myosin interaction and cross-bridge formation. The more actin-myosin cross-bridging, the more tension, or force, that can be generated. Generally speaking, for the heart at least, the greater the muscle cell length, the more overlap there will be, and the more force that can be generated. This is depicted here by this experienced archer with a much longer draw length. This will allow her to shoot much further, just like how stretching a ventricular muscle cell will allow it to generate more force. In skeletal muscle, cells can be overstretched to the point that overlap, and therefore force, will actually decrease. This is less of an issue in the heart, though, as ventricular muscle is much stiffer than skeletal muscle and harder to overstretch. In addition to maximizing overlap between actin and myosin, stretching of myocardial cells will also increase the calcium sensitivity of troponin C and the amount of calcium released from the sarcoplasmic reticulum, both of which will contribute to a stronger force of contraction. Our experienced archer has a carton of milk at her feet and an accompanying milk mustache to help show this. So, how does all this talk of individual cells matter to the function of the heart as a whole? Well, you can actually extend the length tension relationship for single myocardial cells to the length tension relationship for the entire ventricle. In this case, the preload, which is the resting length from which a muscle contracts, will be the end diastolic volume. Our archer is preloaded with arrows that have red fletching, like oxygenated blood that is about to be ejected, to help you remember this. The afterload, which is the force opposing a muscle contraction, will be the aortic pressure for the left ventricle or the pulmonary artery pressure for the right ventricle. This is why this aorta-like tree is serving as a backstop and opposing the flight of these red-fletched arrows. To summarize, as venous return increases, such as from giving IV fluids, the end diastolic volume, or preload, will also increase, which in turn stretches the ventricular muscle fibers. This stretching leads to more overlap and cross-bridging, which generates a greater force of ventricular contraction. This increase in force translates to an increase in the stroke volume and therefore cardiac output. This is all represented by this arrow boy in a blue tunic who is returning arrows with blue fletching, like deoxygenated blood, and his friend who is preloading another quiver. In essence, they are setting the pace at which arrows can be fired, just like how the preload determines the force of contraction and cardiac output, or how much blood can be ejected. So, as venous return increases or decreases, cardiac output will increase or decrease to match, and blood flow through the cardiovascular system will be maintained. And that's it for the Frank-Starling relationship in cardiac muscle. It's a relatively simple concept to understand, but is very important and sure to come up a lot. Before we head out, let's take one last quick look at what we've learned. The Frank-Starling law is based on the length-tension relationship in cardiac muscle, which describes the effect of increasing ventricular muscle cell length on the force generated during contraction. It states that the degree of force a cell can generate depends on the amount of overlap between the sarcomere's thick and thin filaments, myosin and actin. For the ventricle, which is much stiffer than skeletal muscle, this generally translates to the greater the muscle cell length, the more overlap, and the greater the force of contraction. In addition to increasing overlap, muscle cell stretching will also increase the calcium sensitivity of troponin C and the amount of calcium released from the sarcoplasmic reticulum, both of which contribute to a stronger contraction. When expanded to the level of the heart, the preload, or the resting length from which a muscle contracts, can be described by the end diastolic volume, and the afterload, which is the force opposing a muscle contraction, can be described by the aortic pressure. In summary, the Frank-Starling law of the heart is responsible for matching cardiac output to venous return. As venous return increases, the end diastolic volume and preload increase, and the ventricular muscle fibers stretch. This leads to more overlap and cross-bridge cycling, and a greater force of contraction, which translates to an increase in stroke volume and cardiac output. Okay, now that's really it. See you next time.